Welcome, everybody. Today we are working on Unit 9. The topic is designing a database. So we're going to learn about the thought process that goes into designing a database, this thing called database normalization, and then the relationships between tables, which really form the whole relational database structure. And not necessarily in that order. We're going to kind of hit upon the topics kind of like in a general knowledge kind of way. And from a practical standpoint, then I'll look at some of the materials that I've provided for you here. If you've looked at the unit in advance of today, which I do like people doing, I did just add a couple of content pieces because I felt the stuff that I had posted there was kind of getting antiquated and needed a revamp. So I didn't take away the old stuff. I just added new stuff to it. And so we will look at that. So a lot of it is going to be looking at the materials that are right here inside the unit folder and going through it on a pretty granular level. I don't know if we'll get to the point of doing the assignment together, but we might. So hopefully that happens because I think that's good when we do it collectively here in the classroom. Once again, the topics are repeated here in the topics for Unit 9 section. I did add a link here, and I thought this was kind of helpful when I was kind of researching how to update the materials. I ended up landing on this page at W3 Schools, and I'm going to zoom in just a little bit here. There we go. And I want to talk about this concept because we do see this acronym when we talk about databases. Now, you can take the MySQL part off of this and just talk about the acronym itself, which is Relational Database Management System, right? And I want you to understand, once again, and we've been talking about this the whole time, that the database is that server that runs in the background on your machine, and that's where all the information gets stored. And then a relational database management system is a piece of software that sits on top of it to allows you to interact with that database, right? So there's a separation. A lot of what we store in the database is basically we drop stuff into tables, and then we set keys and foreign keys and things like that. And every time we set up, let's say, a foreign key, we're connecting a table to another table, right? And for forming what we call a relationship between one table and another. They do mention here that RDBMS is the basis for all modern database systems, and they do list MySQL in the mix, but some of the other prominent products that are out in the field and used professionally, Microsoft SQL Server is one of the big ones for enterprises that are very Microsoft heavy, and a lot of them are. Very, very common database system. MySQL, of course, is one that's a little bit more web-centric and open source. Also used for a lot of professional work. In the web world, that is the preeminent database by far. Then we have Oracle, which is a private company proprietary system. MySQL is basically the free version of Oracle. And then we have Microsoft Access, which is the lightweight version of Microsoft SQL Server. And it is fine for professional tasks, but it does not hold nearly the amount of data, by the way, that SQL Server can hold. And therefore, a lot of database professionals usually stay away from it for that reason. But it is a really cool product and powerful if your databases aren't ridiculously huge. Right, so a lot of companies do use it. It's also included as part of Microsoft Office, so you don't have to pay extra for it. So Access, it's not exactly free. SQL Server and Oracle are expensive proprietary enterprise-level database systems, and MySQL is the free version of Oracle. There's no cost to it at all. All right, when we use a relational database management system, we do have to use SQL code in order to interact with it, and that's what we've been learning all semester long. So we've had a solid 8 weeks of instruction on how to do that. And think about all the stuff that we've learned, right? We've learned about tables. We've learned how to create tables, put information into tables, extract information. run subqueries. We've learned about data types. We've learned about functions, right? And summary queries and all that stuff, right? And now we're kind of like circling back to the beginning again. And I think like this is a really valuable thing to do when you're learning something is like when I first started talking about this stuff at the beginning of the semester, it probably was like in one ear, out the other. Maybe you kind of got it, maybe you kind of didn't, right? Real frankly, and that's okay, right? I get it. I've been there. Like you take the class and then 2 weeks later, it's like, what was that? I forgot, right? So here's the reinforcement. And mark my words on this, like the more you kind of do that, like you reinforce like what is a database table and that kind of stuff, it really does deepen your understanding when you come back to it later in time. So normally what we define a table, it says a collection of related data entries that consists of columns and rows. So and we call this typically tabular data, right? And you notice each row has information about a specific entity, right? And each row is basically one record in the database table. We have columns. The columns have data types, right? Some of them are primary keys, some of them are not. But whenever we're entering a record for an individual or an entity into a database table, it occupies one row of information. And they have an example here. We've looked at these examples many times over. All right, so this table has 5 records, whatever. All right, so then we start to talk about what is a relational database. And then we realize that databases do typically have more than one table, right? You can have a database that just has one table. That's fine. If you want to do it that way, there's nothing wrong with that. It's basically a spreadsheet at that point, but a spreadsheet with rules, right? Like in a spreadsheet, if I want to put a number in a column and then put a word in a column, I can do that. In a database, it wouldn't let me, right? Because the data type enforces it. But the point of this is, right, that we form relational databases by taking columns from one table and connecting them to columns in different tables. So for example, here we start looking at the customers table where the customer ID, and this is a primary key here for this table, a unique identifier for that content. Notice how they have it highlighted in green, right? So I can uniquely identify any entry in this table with that customer ID. Then I go to my orders table, and instead of repeating all of my customer information here, I now just have to refer to my customer ID, and then that connects it back to my customer table up here, right? So let's see the green. And then I notice here on the far side that I have an employee ID, an order ID, a shipper ID, and notice how the shipper ID is also highlighted. And if I scroll down here, that connects me to the shipper table, right? And so when I want to see how this order shipped, I would use this ID and I would look down here and say, oh, United package, right? Assuming UPS for that. Now, given the fact that there's also an employee ID and an order ID, there's a very good chance that these columns link up to other tables in the database. And this is the power of a relational database. Ultimately, the grand point of it is whenever I have a customer I'm dealing with, I don't need to have all their information in this table also. It's in a different table. I just need a reference back to it. I don't need to have all the details about this employee that maybe sold them the product or dealt with the order, right? I have that in a different table. I don't need to know like the name, the phone number, whatever, about the shippers either, right? That's in a different table. And that's the whole point. The fact that we separate out that information also kind of leads us to this concept of normalization, because that's really what normalization is all about, is to make the data as efficient as possible so we're not repeating information over and over again. Could you imagine like if you have to go in here in the orders table and then like you'd sell something to this customer and then I have to type their name again and their address again and the phone number again and their city, state, zip, blah, 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 all their stuff. It makes no sense, right? They're already in there. They're in there. We just link to them. That's the relationship. So I just kind of wanted to kind of ground us by looking at that first, so we remember those concepts. And what we're going to do next is we're going to kind of look at database design and how we do that effectively and how we build that up. I do want to point out that I released all the old exercise videos. If you guys, if we don't get to the point of covering all this stuff here in class today, we should be able to, so we'll see, you know, you can see it varies on the group how long it takes. I do have the old PowerPoint here too that covers some of this material if you want to look at it. But let's take a look at this database design entry here and look at some of the tips that come with it. So the first thing it says a relational database system should model the real world environment where it's used, right? The job of a designer is to analyze the real world system and then map it onto a relational database system. So this is kind of interesting because this is maybe the first time we're really talking about the roles of database people. Like if you did this as a profession, right? What would you actually be doing? You know, if you were a person that is building the database from scratch, and this is kind of an interesting thought, how do you do this? You know, like what tables do you have? And so for example, when we look at like the guitar shop database, we think about it as like, okay, well, we have guitars, you know, we have orders, we have customers, all that kind of stuff. And all of those things kind of represent some sort of a real world thing, right? Like, and you know, maybe it's an online business, maybe it's an in-person business, it doesn't really matter, but there is some real world entity related to it. So for example, if I was putting products in my product table, I assume I have that in my business, right? So why would I put something in my database that isn't in my business? I mean, it's that kind of thing. Or if I have a real customer, why do I have them in the table? Well, because they're a real customer. I'm not going to throw in people that aren't, right? It makes no sense. So you do have to analyze what are all your information points. And for every organization, it's really different. Think about like how a retail store would operate, and then think about like the databases we have here at Gateway that hold your information. What information does it hold? Well, who you are, right? What degree you're taking, your grades, your payment information. You know, you can think of a bunch of different things that might be involved. Here they have the tip, right? In a table, a relational database typically represents an object or entity in the real world. Each column of the table is used to store an attribute associated with the entity, and each row represents one instance. So if I'm getting customer information, what information is important? Well, their name is helpful, right? Knowing how to get a hold of them is probably pretty helpful. If I'm shipping stuff to them, their address is helpful, right? That type of thing, right? And just to break apart the terminology here, like a customer is like representative of a human being, right? Or maybe a company. I guess it could be a company too. Companies have names, they have locations, they have contact information. People do too. And so we can capture that information in our database. What of that is required is really kind of on the database designer. But I would say like if you had an online business, you definitely want their name, shipping address, email address, and maybe a phone number. All of those things. All right. It says to model a database, we use this thing called an entity relationship diagram or modeling. And there's an image of one here. We're going to create some of this stuff here in just a little bit. But I want to show you this example, and I'm going to try to zoom in one more click here, see if that helps. There we go. That's pretty good. The image is slightly blurry, so I apologize. But with this image, really what we're showing is that when you have a database that's got a bunch of tables, and the tables are connected through things like primary keys and foreign keys, we can actually visualize that. So for example, when we work inside of MySQL Workbench, there's a way that you can generate an image like this for the database that you're working on. So if your database has 2 tables or your database has 50 tables, you can generate this image. And I want you to notice that it lists all the fields, their names, the data types, and their size. And then there's these little connectors here, and it's really hard to see in this image, but we'll see it on screen in a while, so don't worry about that. There's these little symbols here. Some indicate a single entity, the other one indicates multiple entities. And the concept is, for example, if I have a customer table, the customers are going to appear in the customer table once, right? We're not going to list them in there 5 times. But then in the order table, they might order from us all the time. So I have one customer in the customer table that links to many orders in the order table. And that relationship is then called one to many, right? And then we have, you know, the reverse that happens, right, where we might have multiple entries in one table and multiple entries in another table. We call that many to many. Or the tables can be one to one, right? So it really depends on the situation. What's useful about these diagrams, especially if you want to think about this as you're designing a database, being able to draw little lines between things is kind of helpful. Going, oh, yeah, this table connects to this table, this one connects to that one. And not only do they connect, but you know, usually they're color coded and they show you which ones connect to what. Really common to take a primary key from one table and make it a foreign key in a different table. If you guys think about like that one exercise where we tried to delete, I think, a column or something or some information from an entry that was a foreign key. In other words, it was a primary key somewhere else. It wouldn't let us do that because then the database relationships break apart, and that's not allowed. If you have a relationship there, it must be enforced. You know, so how do you form those relationships? In terms of SQL code, you set things up as a primary key and you set things up as a foreign key, and that's how the relationships are forged, right? It's those mechanisms that make it happen. So we kind of have been doing it all along. We're utilizing databases that have been already put together. Now, let's talk a little bit about the relationship types, because there's a few basic ones here. And I'm just going to reinforce what I just said, which is the connections in a database are managed using primary keys, right? And they call this a unique ID for a row in a table. And then foreign keys, a column in one table that references the primary key of another table. So like in my orders table, I have my customer ID. It's not a primary key in the orders table, but it is a primary key in the customers table, right? And once again, that forms the relationship that we're talking about. The first relationship that we learn about is the one-to-one relationship. And so in other words, if we have one table and we have an entry and there's a one-to-one relationship, let's say they're using table A and table B, right, as an example. That means that the one entry in table A is directly linked to the one entry in table B, and you cannot have any more in either table that refer to the same connection, right? And and I want you to notice what it says here. This type is less common, but is useful for splitting a large table usually for security reasons. So for example, I might have a table where I list your name and your email address, but maybe your address is stored in a separate place because not everybody at the company needs to know your street address, right? Or maybe in our database, you have your social security number, and we might have one table that just holds social security numbers and only certain people get to see it, not everybody, right? So that's a good example of when we might do that. All right. They do kind of indicate, right, some examples here so you can read through those. But let's take a look now at the one-to-many relationship, which is the more common type of relationship we see in a database, by the way. So with this approach, and notice the example they're using, customer and orders. And that's a great example, right? So we have a customer table that holds a list of all of our customers. Each customer appears in the customer table once, right? But they can go to the orders table and they can put in as many orders as they want. So the relationship is then called one to many. In the customers table, the customer ID is the primary key. And then in the orders table, we have a foreign key, which is the customer ID, which ensures two things: that the customer is for real because they're in their customer table. And then we can link all of their orders back to that customer then using that relationship, right? And this is pretty intuitive when you think about it. And that's why this is one of the more common types. And really why, I think relational databases were formed in the first place. It's like, oh man, do I got to repeat all this customer information again? We know your address and phone number and stuff, right? And think about this, like even back in the paper and pencil days, and I happen to like work in wholesale businesses back in the pencil and paper days, and we would get calls from our customers, and they would say, "Hey, this is Joe at whatever. Can you send me 10 cases of that and 5 cases of this?" And I wouldn't ask them for their name, address, and phone number because we already had it in our Rolodex, right? I would just take their order, hang up with them, and then go look it up and add it to the order form, right? There's no point in kind of redoing that information. That's the point, right? Why we do that. There is also a many-to-many relationship. And a really good example, and I think the one that they're pointing out here is an example, right? So like where we have a table that might hold students and a table that might hold the courses they would take, right? If, for example, if I'm a student, I might sign up for a bunch of courses next semester, 1, 2, 3, 4, 5 courses, something like that. And then from the course perspective, I'm going to have multiple students, right? So I have one course listed, but multiple students are taking that course. It's not just one student, right? It's not like the order and customer relationship. Here's a relationship where either table can link to multiple entries on either side. Makes sense, right? Like we get a bunch of students taking a course, and therefore we have a many-to-many thing going on. Okay. I want you to notice here, this bullet right here. It says how it works. You cannot implement this directly. This is kind of weird. You must use a third table, often called the junction table or linking table, to make this happen. So they give an example. So the student table has a primary key, which is the student ID. The courses table has a primary key, which is the course ID, right? Now, those both make sense. But then we create a junction table called enrollment that has 2 foreign key columns. One points to the students, one points to the course ID. So their primary keys elsewhere. And then that enrollment table, a third table, is basically kind of the broker for the connection between the two tables, right? It allows the course to have many students. It allows the student to have many courses. So it's kind of like bidirectional. And then, for example, a single row in the enrollment table might have like the student ID and the course ID. It links one specific student to one specific course. And then, of course, that student could have multiple entries there, and that course will have multiple entries there as well, right? All right. Next. Now we're going to talk about this concept of normalization. And I am grabbing a Kleenex here to blow my nose, and I apologize that I have to do that while the recording is running, but I'm going to pause. All right, so now we're going to touch upon this concept of what we call normalization. And this is a weird concept, right? To consider that data can be normalized. Like, what the heck does that mean? But really, what it means in terms of a database, as it says here, is the process of organizing data to reduce repetition and improve data integrity. So think about it like this, right? And I'll use kind of a real world example. Go back to my example about taking an order from a customer, right? Customer calls up, they know we have their info already. They don't need to give me their address for shipping and stuff again. They just call and say, hey man, I want 10 cases of whatever, 10 cases of coffee, send it to me, right? Then I go to my database or Rolodex or wherever I store their information and grab it and put it on the order form. But prior to using that sort of an approach, what if, every time you took the order, you get their address. And then what if one of these times somebody puts the address in wrong or the wrong zip code or something weird like that. And now the customer that's ordered many times with us before is getting their stuff sent to the wrong address, right? Why did that happen? Because we're repeating the information probably on the order table, or order form, if you want to think of it that way. And that just increases the possibility of errors happen. So that this is one of the reasons why this exists. So normalization is what we think of as a process. I talk here about first, second, and third normalization form. Most database designers don't really take it beyond that form. There is fourth and fifth normal form and a couple of other form factors that you can apply to databases. First, second, and third normal form are considered normal in a database design to eliminate like redundancy, inaccuracies, and basically make sure the data is correct, really is what it's about. So first normal form, and you can see the little topic here says make it atomic, okay? And so the most basic rule has these two requirements. Each cell must have a single atomic value, meaning no lists or repeating groups in one cell. Okay, so I'm not going to list the person's name twice or their address twice, right? Or something like that. Okay, so, but think about this. I can have a customer named John Smith, and I could have another customer named John Smith, and they both have the middle name of Mark. And oh my God, they both were born on the same day, et cetera, et cetera. That happens, right? For those of you in my Python class, what do we I think we have like two Walters, two, whatever. And I don't need to like name people. But that happens to me all the time. They don't have the same last name, but think about that, right? It is possible to have the same people with the same names. So this is why we create ID fields, right? So that meets bullet number 2. So each row must be unique, which is usually handled by having a primary key. And the modern good practice on this is to apply an ID basically to every entry in your table, whether you use it for something or not, right? But if I do have, for example, multiple John Smiths, then they would each have their own customer ID number, which is the thing that would make them unique. Now, they're showing here in this first example how something is not in first normal form. A table where one cell has a list. So for example, if somebody's ordering a product, it doesn't really make sense. So if they ordered like apples and then they ordered bananas, and then they ordered oranges, right? To list those all together. It makes more sense to split those apart, right? And if you think about our guitar database thing, they do kind of the same thing where they have an order ID and then they have an order items ID where they take the order and they break it down by items, right? Like last thing you want to do is get an invoice or a receipt where all the items are listed on one line and all the prices are combined. You see what I mean? Right? It makes more sense to itemize everything because it's a lot clearer. So moving from combined information to separated information is considered first normal form. There's also second normal form, and it says this only applies when you have a composite primary key, meaning a primary key made of two or more columns. And this is something that does happen, by the way, right? So maybe I have a student ID combined with last name, or a student ID combined with last name and first name, and combining three columns together, right? And it says the rule says the table must be in first normal form first. So all your data's got to be split apart as much as possible. And every non-key column must depend on the entire primary key, not just part of it, right? All right, so let's look at a bad example. Here's a little listing where we have a composite primary key of the student ID and the course ID are put together, right? And notice that this ID and this ID are kind of linked together. So these together form the primary key, right? And notice how the student then has another entry here. And notice the student's name, right? Different grades for it. Okay, so the problem is that the student name only depends on the student ID, not the full key. So in other words, they're saying that this piece of information really only depends on the student ID. It does not depend on this at all, right? They call this a partial dependency, and it causes the redundancy Alice is repeated for every course she takes, which is not really a good thing. So in other words, this piece of information, the student name, becomes redundant in the table. This is kind of like putting your customer's address in with every order. It makes no sense, right? So what do? We split the table to remove the partial dependency, right? So we form an enrollment table. So we add another table that handles those things, and that records the student ID, the course ID, and the grade. The name is not included. The name can be extrapolated from the student ID, right? That would be the point. All right. All right, so then we go to third normal form. And this says that this applies to the columns that are not part of the primary key. So this involves you kind of like studying the tables a little bit, by the way, to figure stuff out. It says the rule is that the table must be at least second normal form first, and that no non-key column can depend on another non-key column. And they call this a transitive dependency. All right, so here's a bad example. It says, let's use the course ID as a primary key, right? So you see they have the course number in there. Then they have the course name, the department name, and the department building. It says the problem is that the department building depends on the department name, which in turn depends on the primary course ID, right? So in other words, the building depends on the name, depends on the course ID. And then if so imagine if the comp sci department moves to building C, you have to update a whole bunch of stuff from your table to fix it. Makes no sense. So in other words, the information depends on other information, which depends on other information. So that's a bad setup. So how do you fix that? We split the table to remove the dependency, right? So we come up with a courses table that has a primary key of course ID, right? And then that holds the name of the course and the department. And then we can have a separate table for departments, which has the department name in the building. That way, if the department moves from one building to another, you update one table in one row, not like 500 entries, every time they offer the course, right? And then you would have example entries like comp sci is in building A and art is in building B. And this is kind of interesting because Gateway has gone through transitions like that. We used to have IT courses at 4 campuses, 5 campuses, right? Now we have IT at 2 campuses or 3 campuses, depending on how you count. And it's changed over time, right? We used to have a big IT department in Kenosha, and they decided 10 years ago to move it here. So all the IT courses are together. So, it does happen. So I want you to notice right here, they say by reaching third normal form, your data is generally considered normalized, right? It reduces redundancy saves space, makes your data much easier and safer to update. And as I mentioned, you can take this deeper if you wish, right? You can go to fourth normal form and fifth normal form, and those get kind of heady and theoretical. So usually in database design, we kind of cap it here. This is usually a pretty good level to operate at. Now, I do have this design guide, and I'm going to dig into this here in just a moment. And let me just ask very quickly here, does anybody have a question about this at this point? You guys all good? All right, pretty relatively clear, I assume? Yeah, I think so. I'm just making an edit to one of my entries here on the other screen. I realized I made a little typo. All right. So I'm going to click through on this link. This is a database design guide that was put together here. And I think Christian Herr originally put this together. If I remember right, he's another one of our instructors. When he put this together, he did this basically using SQL Server as the model database. So that's kind of interesting, but here's what's cool about it is it doesn't matter what database system you're using, the concepts are really exactly the same because they're all relational databases. And he goes through this process of explaining database design, and he kind of digs in pretty deep. So I think this is a pretty handy document to look at. I'm going to rifle through it kind of quickly, and then we'll move on to the next topic. But notice I like his bullets at the top. It says database design is a process in creating the proper structure of database tables, the relationships between those tables, the appropriate data constraints, so having the right data types and size and stuff like that, and other structural components, right? And some of it might be linking tables, some of it might be, what's a foreign key, what's a primary key. 3 design approaches you can use. And I think this is very helpful too. You might already have information, right? So this is kind of an interesting thought. And this happens to a lot of businesses. They gather information and they throw it into a spreadsheet, or they're using a piece of software that generates something like a table or a spreadsheet or a CSV file, and they have that data available to them. And then they want to ask questions about the data and they need to do queries, but they don't have it in a database, right? So they use data that already exists. Sometimes it comes from one singular source, literally a single table, or, the accounting department has info about this, the registration department has info about this, et cetera. The advisors have information about this. We can pull all the data together and make it into a database. Also, you can start a database from scratch. That's number 2, right? So design for new systems where you don't have any data yet, and okay, example, I'm going to let's say I really open up a guitar shop, whether it's retail or online. What information do I need to have in my database? I don't know. I haven't done the business yet. But you can imagine that you'd have customers and products and shipping and all of those things. So you can conceptually design something in advance, even if you don't have data. So you can start from 0. Another approach is to look at a database that already exists, that already has tables of information, but its structure might not be optimal, right? Like the relationships aren't good, the keys aren't right, it's not normalized, it's got too much old information in it, the information's not consistent, the data types aren't enforced. I mean, you can go on and on with the problems of a database that already exists. So all 3 of those are things that you might do if you go out into the workplace, right? And need to build a database. One thing I always challenge my students to think about, and I sometimes do this for myself, is like, do I have things that I do in my personal life, for example, that would benefit from storing stuff in a database? Okay, here's an example. I have like a big collection of music gear that I collected over the years of being a musician and whatever. And then I got to the point where I realized my collection's pretty large, how do I keep track of it? Well, I could write it down in a notebook, right? I could, as I do right now, just write the information into a spreadsheet. So I'll have like, what it is, the serial number, a little description or something like that. So I have existing data, but maybe it would be really useful if I have a lot of stuff to put it into a database. Like maybe a better example would be if you have a collection of books, or if you collect music, or if you collect, I don't know, plushies. I don't know. Like what's your thing that you collect? You could make a database about it, you know. So think about that. All right. They have examples here. Like if you're designing from existing data, right? Often you might have files, documents, text files, spreadsheets, and that can lead to your database design. Or you have some other database system, like here at Gateway, we might have an ERP system or a CRM system. I think we have both. And we can extract information from those other databases to build a new database that does something different, right? Or, maybe replaces the old ones. If you're designing for new systems, well, then you think about, what processes might feed your database. So like, here's a really common thing that happened in the last 20, 30 years. A lot of businesses went from operating on paper to operating on computers. One of the best examples of that is like your doctors. When I went to the doctor when I was younger, even when my kids were younger, they would write everything on a piece of paper and put it in a folder and put the folder in a file cabinet, right? It really has been only the last 10, 15 years that now you go to like your doctor and they type it all in, and you might be able to access your chart online as a database. So they went from like a paper-based system to a database. So that's a really common conversion. So if you have a business, either that's brand new or one that operates on paper, switching it to a database design helps a lot. So they look at the forms they use, they look at reports they generate, and then they talk to the people in the organization to say what would be good in the database, what would be helpful for you. And then they look at what other people have done in the same space and create first a model of the data, so they can figure out what the tables are. And then they transform that into a design and then build the actual database. If you're redesigning a database, right, you might do what they call migration. And this is a common thing that we do in the database thing. So migration is kind of like we're copying one database to another, right? And then after we make the copy, we tweak it. Or we have one database that handles this, a different database that handles this. Let's migrate both of those into one new database. That's a thing you can do too. Right. So migration is kind of another way for saying copy and combine. As you can see here from the graphics. When we start to talk about tables and relations, there's some words here that I think are interesting, because normally when we talk about tables, we talk about the top row, we talk about the table, we talk about the columns, and we talk about the rows. The table is the whole thing. The column is the one entry, like customer ID or first name, last name, that kind of thing. And then a row is a record that contains all the columns for one entity. The blue row, right? This is another way. So like you can think of a table as how it relates to other tables. You can think of the column as an attribute or a feature of the entity you're looking at. Like my last name is one of my attributes. My ID number is one of my attributes, right? And then for the row, we look at the tuple or the collection of information that is relative to me. And tuple implies unchanging, by the way. The old-fashioned way to look at it is we used to look at tables as files, like a spreadsheet, that a column was kind of a field, right? And that a collection of fields for one entity was called a record. So these terms, so the point is Table, relation, and file kind of go together. Column, attribute, and field kind of refer to the same thing. And then row, tuple, and record kind of refer to the same thing. I was always kind of taught, real frankly, with the top row and the bottom row. Like when I was getting into it, tables and files are interchangeable. Columns and fields are basically the same thing, and rows and records are basically the same thing. The in between really kind of focuses on the relational aspects and constructs. For those of you that also in the Python class, right, and I know many of you are, and often take this at the same time, a tuple is a data structure I think we're learning about tonight, actually. I forget what our topic is tonight. If it's not tonight, it's next week. But it's basically a data collection of an entire collection of stuff, right? We talk about important relationship terms here, a lot of the ones that you hear here. So relations, dependencies, composite keys, primary key, surrogate key, foreign key, referential integrity constraint, normal form, and etc. Right? And there's a little explanation of each one of these down here that you can read through. Then we have this little table here that explains the characteristics of relationships that you can read through if you wish. And I think this is helpful because sometimes it's pertinent, sometimes it's not. And you can read through that yourself. I don't want to go through each particular one. And then they show examples of information here that are normalized. And I want you to notice, for example, a normalized table, all columns have a single data, right? They're unique. Usually we use the ID number or something like that to make them unique. The rows contain data about the entity, right? All entries in each column are of the same kind. Yeah, and notice they say here, due to many missing data in the comments, this table could be normalized further by moving the comments into a separate table. So these might all be separate comments here. So this could be put somewhere else. So we could have a table that's just a comments table, right, to normalize this further. So we could get rid of the comments, simplify the information more, and the comments are somewhere else. Another thing that they talk about is like, what does an unnormalized table look like? Why is this one unnormalized? Well, if you look at the phone number column, some of the entries have multiple names or multiple phone numbers in the phone number column. And their point is you should just have a phone table then, right? Because that way, otherwise, how do I get all the phone numbers in if it only allows you to enter one phone number? Right? Do I really want to have a collection of phone numbers in there? Probably not, right? So that would be considered unnormalized. The other thing, this one is also unnormalized. Notice what they did here in this table is like they leave all this stuff blank and they're really just leaving it blank so they can put a descriptor here on fax and home for the phone numbers for Tom. And right, you would do this maybe in a spreadsheet. You don't do this in a database, right? And that's kind of the point, right? And that's where a lot of the problems really crop up from is when we're working in data or a spreadsheet and it makes sense in the spreadsheet and then we move it over to a database. In the database, it does not make sense. And so what they recommend, right, ultimately, like for the phone number problem is not only do you have a separate table for it, so that the phone table would have its own primary key, then a foreign key to make sure it links up with an actual person, and then you list the phone number, and then you can designate what kind it is. Is it mobile? Is it your office? Is it fax? Right? And that would be considered normalized data. We also have this concept that we call functional dependencies. So sometimes, for example, I might have information in my table that exists because of information in a different table, right? Like if I want to like calculate the shipping cost for something, I might need to look at all the individual order items in an order item table that relate to one order in my orders table that relates to one customer in my customers table. But in order to get the right shipping cost, I have to have access to the customer order items and then break those down individually and combine them. And if that piece of information is missing, then my table here doesn't have the right information. So that's called a functional dependency. That's a primitive example, but sometimes it is a direct correlation. And if that information connection happens across tables, right, this is what happens, right? You know, you have that probability that it might break. And so they walk through the process here, figuring out the determinants, like what is the one thing that determines another. And they kind of break it down. Like, for example, here they talk about the SKU description, and they look at what might be a key and what might be a candidate key, meaning does it rely on something else? And then there's a series of questions here. And we will, by the way, we don't get this deep in our homework, but I think it's kind of interesting information to kind of keep in the back of your head. And it's a reference material for you going forward. But the keys really in the definitions here at the bottom of the page. And a determinant is a column used to determine values of other columns, right? So if I need the shipping cost, but it's dependent on me multiplying the number of things ordered by the shipping weight, by the that kind of thing, that's a determinant. A candidate key is a determinant that determines all columns. That's pretty rare, but it does happen. And then the primary key, of course, is something that we know about, makes each thing unique. Then they go through the normalization thing here, which we just talked about. And then they show you how to do it in SQL Server, which frankly is not relevant to us anymore. But if you're curious, there is that information. All right, I'm going to take us back to the course shell here. I'm going to try to finish off the lecture material, then we'll take a break. So we're going to go a little bit past the halfway point here, if you guys don't mind. So we talked about relationship types. We talked about normalization. We took a look at the database design guide. And there's another link here on normalization. And I'm just going to take you out here. I'm not going to talk through this, but this is from W3 Schools in a foreign country, by the way, I think from India. And they talk about first normal form, second normal form, third normal form. I do want you to notice here, they also have material on fourth normal and fifth normal if you want to read up on it. Then they also have the Boyce-Codd normal form, which is a different approach to doing it. But the top three are still the ones that most database design is really kind of aiming for, is those top three. In some really, really large database systems, you will get database engineers that try to push it all the way to fifth normal form, because it does help with like super big, robust databases being more efficient. And then there's this other Boyce-Codd approach, all of which are detailed and explained here. And then, of course, you can always dig further by doing your own research. I just want to point out the fact that I do have that here in the course. I'm not sure if that covers the remainder of the all right, so we have an unnormalized sample table here. And I'm just going to click through this really quick because this is very, very similar to our homework, so we can revisit this. But it shows this process of going from basically a table that is unnormalized. And as you look at this, and I want you to think about this, as you look at this table, you would look at this table, like if you were brand new to database design, maybe even still, and go, yeah, this looks fine. This looks like a fine database table. What's wrong with it? Looks like it's got an ID, there's a name, date of birth, department, title, pay code, and description. Okay, none of that's bad information, is it? Right? All right, but if we do first normal form, what we'd look at here is we do have an employee ID, but it wasn't necessarily a primary key. So the first thing we do is we set a primary key. So what's the first step of normalization? Make sure your records are unique. One easy way to do it is to add a primary key, usually in a unique column, right? And the ID field is a wonderful way to do it. Then we go to second normal form, and we start to look at the information that was originally in the table. And I'm just going to pop back here for a second. So like, I don't know, date of birth, age, okay, that might relate to an employee, but what department they work for, their title, their pay code, and a description, those are things that we could break out to other tables. So I might instead have a department ID, right? And I just list the departments in that table. I might have a title ID. I might have a pay grade table. I might also have a job description table as well. So I took that one table, and by just going to second normal form, I added 4 more tables, but now the information doesn't repeat as much. And look how much simpler the employee table is, right? Still refers to the information in the other tables, and be mindful of the fact that each one of those has a primary key, and that certain pieces of information have to become then foreign keys in the employee table. So the department ID here in the department table becomes a foreign key for here. So in other words, I can't put it here unless it exists in this table. So that would be considered second normal form, right? Then we go to third normal form. And in third normal form, if you remember, like look for combined information. Originally, they had first and last name together. Is that really wise? And by the way, where's the middle initial or middle name? And now in a lot of databases, what else do we put? We have columns for titles, columns for pronouns, right? Like people want with certain pronouns on their name, and that's fine, but those all have to be columns, don't they? Right, so that would be third normal form, is breaking the data apart, right? And I think that was just a little experiment. So that's a really good example of what we're about to do in the homework, by the way. And I'm just going to bop us back, and I think we're about to take our break here, if I'm not mistaken. So I'm just kind of reviewing all the content. Yeah, we're going to go into homework next. So this video is going to end here, folks. We're going to take a break. I'm going to release the assignment so we can work on it. In fact, I'll just do that right now. And this video ends here.